The paper explores a novel method for measuring the average temperature of the X component in type II core collapse supernovae. By measuring neutral current incoherent neutrino-Argon interactions in DUNE, researchers can obtain spectral information for the combination of all active neutrino species. Combining this all-neutrino spectral information with detailed charged current measurements of the electron-neutrino and electron-anti-neutrino fluxes from DUNE and Hyper-Kamiokande, the average X temperature can be inferred to within a factor 2 for most cases and to 30% for a small range of average X temperatures. The methodology for modeling the neutral current measurements involves three key components: the supernova neutrino flux as a function of neutrino temperature, the cross-section of the NC interaction, and DUNE's detector response. The supernovae neutrino differential flux is modeled using a Fermi-Dirac spectrum, assuming a progenitor of 10 solar masses at a distance of 10 kpc from Earth as a benchmark. The characteristics of the NC channel do not allow for accurate measurements of the neutrino energy spectrum, but they provide enough discriminating power to reconstruct the average X temperature. The paper highlights the importance of flavor nonspecific information from supernovae neutrinos, which is crucial to understanding the neutrino flux emitted without uncertainties related to neutrino oscillations, matter effects, or neutrino self-interactions that occur within the supernovae. The authors also examine the efficacy of constraining NC cross-section uncertainties on improving X measurements, finding that if additional measurements of M1 plus excited state transitions in argon are able to reduce correlated cross-section uncertainties from 15% to 7%, the size of the 1 sigma allowed regions for TX becomes sample size limited, approaching the case where there are no uncertainties on the cross-section. Here is the combined summary. The analysis focuses on using expected neutral current (NC) events to measure the average temperature of the neutrino flux without considering a pinching parameter. For neutrino interactions on argon nuclei, the most recently published NC cross-sections from W. Torno et al. Are utilized, with a 43% theoretical uncertainty composed of 15% uncertainty on M1 inch measurements and 40% theoretical uncertainty due to differences derived from choice of shell model calculation. A fractional covariance matrix is constructed to account for the uncertainty in the cross-section, varying with input neutrino temperatures and computed at approximately every 2 MeV of temperature. Trilinear interpolation is used to generate the necessary fractional covariance matrix. The detector response and reconstruction efficiency are also modeled, with DUNE expecting 15% energy resolution in their TPCs. A response matrix is calculated to capture the detector's response to NC events for the nu and N cross-section channels. Efficiency cuts are explored using the distribution of deposited energy per unit distance traveled in the detector to separate NC events from charged current (CC) events. A dx distribution for electron and photon-like final states is used to scale the normalized distributions to the expected event rates in the NC and CC channels. A cut in the dx region of 3.1 MeV per centimeter includes 95.26% of the signal events while rejecting all but 15.83% of the background CC interactions. The expected reconstructed event rate in DUNE FD is shown as a function of nu X temperature, combining the NC cross-section, response matrix, efficiency cut, and flux for specified neutrino temperatures. The goal of this analysis is to demonstrate reconstruction of the nu X temperature by combining NC channel measurements from the DUNE FD and constraints on nu E and NE temperatures from CC measurements in DUNE and Hyper-K respectively. The research paper presents a novel approach to measuring the average temperature of the non-electron flavor X neutrino spectral information from type II core collapse supernovae events using incoherent neutral current (NC) interactions in the DUNE FAR detector (FD) modules. This analysis combines the expected incoherent NC sample from DUNE FD with constraints on the electron and non-electron flavor temperatures from charged current (CC) channel measurements of the DUNE and Hyper-K experiments. The paper utilizes a Binetlog likelihood method to explore the sensitivity of this combined analysis to the X temperature, with the addition of statistical constraints on the electron and non-electron flavor temperatures and cross-section uncertainties. The analysis demonstrates that the discrete excitation nature of the NC interaction channel prevents the resolution of the energy spectrum from supernovae neutrinos, but general parameters of the fluence can be measured to the 1 sigma and 2 sigma levels. The paper presents 3 scenarios with different cross-section uncertainties, including a case without cross-section uncertainties, a case with full cross-section uncertainties, and a case with reduced cross-section uncertainties. The results show that the combined analysis can measure the average X temperature to within a factor of 2 in most cases, and to within 30% in the best case. The analysis also highlights 2 distinct degenerate regions in the measurement space, primarily caused by the discrete gamma-ray energies of the NC cross-section and the uniform fluence across the energy range of the NC events for X temperatures above approximately 8 MeV. The paper concludes that modest improvements to the argon B, M1, measurements provide substantial improvements to the X temperature sensitivity. The findings underscore the power of NC measurements in measuring X spectral information from type II core collapse supernovae events, despite technical challenges and small sample sizes. Here is a combined summary of pages 7 and 8 of the research paper. The authors discuss the potential of the Deep Underground Neutrino Experiment, DUNE, to measure the average temperature of the supernova nu X component, which is critical for understanding supernovae neutrino emission. By reducing correlated uncertainties from 15% to 7%, the TX measurement becomes sample size limited, approaching the case where there are no uncertainties on the cross-section. Combining neutral current, NC, measurements of neutrinos on argon with NC measurements of neutrinos on carbon from Juno could provide stronger constraints on average TX temperature reconstruction. The authors acknowledge contributions from various researchers, including Janet M. Conrad for insights on liquid argon TPCs, Anna C. Hayes for modeling neutral current cross-sections, and funding support from the NSF Graduate Research Fellowship and the U.S. Department of Energy. In the appendix, the authors discuss the prior assumption on TX, which is critical for deriving credible regions for the average temperature of the supernova nu X component. They demonstrate that a uniform prior on Tx between 0.1 MeV and 300 MeV results in a degenerate region of allowed Tx temperatures, which can bias the expected sensitivities. To avoid this, they apply a prior that allows only values of Tx below 60 MeV, motivated by supernova simulation studies, neutrino-induced nucleosynthesis, and diffuse supernova background searches. The authors show that relaxing the prior assumptions on Tx significantly widens the allowed regions below 60 MeV for injected Tx between 1 MeV and 5 MeV. However, the width of the allowed regions considering the full Tx parameter space up to 300 MeV remains largely unchanged outside of this region. The results highlight the importance of prior assumptions in deriving credible regions for the average temperature of the supernova nu X component. Here is a combined summary of pages 9 and 10. The expected credible regions for T_X are presented in Figure 12, showcasing the Asimov credible regions as a function of injected T_X values, assuming average neutrino temperatures of T_E equals 3.3 MeV and T_VE equals 4.6 MeV. Notably, the uniform T_X prior extends up to 300 MeV, differing from the previous credible regions in Figures 8, 9, and 10, which were limited to T_X values below 60 MeV. Figure 13 illustrates the fractional width of the 1 sigma credible regions, comparing the width from the hyperbolic tangent prior, solid lines, to the widths obtained from the uniform prior, both below 60 MeV, dotted lines, and up to 300 MeV, dashed lines. The 3 colors in the figure correspond to the 3 cases of cross-section uncertainties, specifically 40% uncorrelated and 15% correlated uncertainties, 40% uncorrelated and 7% correlated uncertainties, and no uncertainties on the NC cross-section. The results highlight the impact of prior choices on the credible regions, demonstrating that the uniform prior with a wider range leads to broader credible regions. The fractional width of the credible regions increases with the injected T_X value, emphasizing the importance of accounting for uncertainties in the cross-section. The comparison between the hyperbolic tangent and uniform priors reveals that the latter yields more conservative estimates of the T_X credible regions. Furthermore, the figures suggest that the choice of prior and uncertainty treatment significantly affects the inferred t_x values, underscoring the need for careful consideration of these factors in future analyses. The assumption of a uniform prior up to 300 MeV allows for a more comprehensive exploration of the t_x parameter space, but may also introduce additional uncertainties.